the syllabus and the list of topics?
Okay. Thank you.
Yeah. Yeah, you're welcome. Okay. So we talked about, hang on, let's see if I got this right. Okay. We talked about the electric field last day. It's a force field. It's a mathematical tool. It's intended to simplify your life, although it's a kind of an abstract thing to get your mind around, to understand. But once you do, it's helpful. So it's kind of a challenge to get there in the first place. But once you do kind of understand what it's telling you and how it helps you, it's good. Does anyone remember what the electric field means? It's related to force, right? So how would you describe the electric field using the word force? Oh, I see your hand up, Robin. We're not hearing you.
Electric force per unit charge.
Exactly. The electric field is the force per unit charge, which is well remembered. Thank you. So if we use the just helpful tool to imagine some hypothetical charge of +1 coulomb, we can pretty straightforwardly go back and forth between electric field and force. Okay, electric field is the force that would act on 1 coulomb if a +1 coulomb charge was there. Okay, so that +1 coulomb is not a required way of thinking about it, but it's a helpful tool in order to think about, the direction of the force on a charge that would be in a position if you knew the electric field there and so on. So we talked about electric field lines and how those represent the electric field. So the electric field lines represent the force per unit charge. So they point in the direction that a positive charge would feel a force if it was placed in that electric field, right? So in this slide here, we've got sets of charges, pairs of charges. On the left, we have a positive and a negative. So if we put a +1 coulomb anywhere near the positive charge, it would be repelled by that and be forced away. It would feel a force away. So that's why electric field lines point away from positive charges. We have to imagine what would happen to a +1 coulomb charge if we put it somewhere in space near this plus charge here or near this minus charge over here. If we put a +1 coulomb charge somewhere near this minus charge, it would feel an attraction. So the electric field represents the force that would act on a positive charge due to the presence of charges nearby. Okay. In this question, can you tell which diagram has the larger charge magnitude?
Would it not be C?
It would be C. Why would it be C?
Since in A those two charges are equal, as the field vectors are like meeting each other. Mm-hmm. This is the same case in B where they're both equal, but in C you can see that the force vectors are only overtook in a small amount of area.
Yeah.
Yeah, that's how I rationalized it, but like that's probably not the scientific way or whatever.
Well, it's got the essence of it. When you see an electric field, so thank you for that. When you see the electric field diagram, the closer the lines are together, like the more number of lines, the stronger the force. So if you look at the positive charge in panel A, you got, I don't know, like 10 or 12 lines coming out of it. But on the right-hand side, there's more arrows coming out of the positive charge. So that means the electric field is stronger. So, and the charge is bigger. It's creating a stronger electric field. It's creating more of a repulsive force against, your hypothetical 1 coulomb charge. Does that make sense, everybody? So the stronger the field, the more lines you have in your drawing. And that means that the charge that's causing that field has to be bigger. Maybe it's more obvious to look at panel B and C. So in B, you've got a lot of space between the lines compared to panel C. So the charge has to be stronger in panel C to create more field lines. Okay, cool. So we're not going to derive this here, but the electric field for an infinite plane of charge is given by this formula here. And we're going to assume that the plane is in the plane of charge is in the XY plane, the coordinate plane. And so the electric field points in the direction perpendicular to the plane. So in this case, it would be k hat. Okay. So we've got something that's super interesting here. So for an infinite plane, very, very large plane with charge density sigma. So we've got charge distributed equally over the whole infinite plane. We have an electric field that looks like this. And it's super interesting because it doesn't have a dependence on position. This formula has no R or X or Z or anything. So this is a constant. So if you have an infinite plane of charge, the electric field is constant nearby it. And you can see in the diagram below here. On the left-hand side, we have a plate or a plane with positive charges distributed across it or over it. We're looking at a side view of it. So this plane extends in infinitely far in the side to side, left to right direction and in and out of the page. So we're looking at a cut through here. So we've got positive charges in this plane. If I brought my hypothetical test charge, my hypothetical +1 coulomb anywhere near here, it would be repelled by this plate. So that's why the electric field lines are pointing away. These red lines are the electric field lines. The same is said for the same can be said for a negative plate. So if we've got a negative plate in the XY plane, and it's got negative charges distributed equally all over it, then if we put a hypothetical positive test charge anywhere nearby, it feels attracted to the plate, so the electric field lines point towards the plate. And notice that it's really hard to see because the arrows are small, but the electric field is towards the plate, above and below the plate. So the field lines converge and go into the plate. If the plate is negatively charged, and the field lines come out of a positive plate if the plate is positively charged, and in both directions, and it's a constant. And you can tell it's a constant in the diagram because all the lines are parallel. There's no place where they get closer, which would mean that the electric field is stronger. So when you have electric field lines that are parallel to each other, equally spaced, that means the electric field is a constant magnitude. Does anybody have any questions about this? So this we're going to take as given here. If you put two panels or two plates together, we saw this diagram before, but we're going to do an example with it right away here. If you put two plates together, you put a positive plate and a negative plate, then we have the same thing going on. Let me go back for a second. If I have this positive plate, I've got electric field lines pointing away everywhere. And if on my negative plate, I have electric field lines pointing towards everywhere. And if the same amount of charge density, like one is positive and one is negative, but if the same magnitude of charge density is on there, or the same magnitude of charge is on there, the electric field magnitudes will be the same. So when I put the plates together, like if I put the negative plate here over to the left, somewhere nearby this positive one, the plus and minus field lines that overlap will cancel each other out. And then the field lines that point in the same direction will add together. Okay. So if I put this negative plate below the positive plate, you can see I've got field lines from the positive plate going down, and then field lines going into the negative plate going down. So if I put the negative plate here, I've got this region between the plates where the field lines both point down. So they constructively combine. But then, like if I put the plate, oh, you know what, I can just draw it. If I put the plate here, my negatives. So the negative plate has electric field lines pointing towards it, and the positive plate has electric field lines pointing away from it. So these two add up because they're in the same direction. The negative plate has field lines, electric field lines pointing towards it, but the positive plate has electric field lines pointing away from it. So outside the region between the plates, or the region outside the plates, the electric field cancels out. If the charge density is the same on both, it cancels exactly. So these two cancel each other out, and the electric field magnitude outside is 0. The same happens here. The same happens above the positive plate. So the positive plate has the electric field lines, pointing away from the positive plate. But the electric field lines from the negative plate down here point down. So these cancel out here. And we end up with the magnitude of 2 times sigma over 2 epsilon naught in between, because they add up. So it's twice as much. We have sigma over epsilon naught in between. Does that make sense? We're relying on the fact here that the electric field of an infinite plate is constant. So it's a very simple addition. Outside the area outside plates, when you put them near each other, the electric field cancels out, but inside it adds up. It combines to add to a stronger electric field. Okay, so this is the thing we're just talking through here. The electric field between the plates is the combination of the electric field from the positive plate plus the electric field from the negative plate, and because they both point in the same direction, they add up together. And outside the plates, the electric fields cancel out to 0. This is a device that you probably will see, especially if you go into engineering physics or electrical engineering. It's a capacitor. It's a simple capacitor. Yeah. If I put a positive charge in here, who thinks it let's see. Let's do a thumbs up. Let's do thumbs up if you think it goes to the right, and thumbs down if you think it goes to the left. Any thumbs up, thumbs up, thumbs up. They're fading in and out here, but I see almost all thumbs up. Okay, what happens? Okay, I see that we have good understanding there. What if I put a negative charge in here? Thumbs up for the right hand if it goes to the right, or let down if it goes to the left. So for an electron, see, and I saw like a high five or something. I don't know what that is. Okay, good. Very good. Is that a rabbit? Thanks, everybody. Gotta take this seriously. Okay, so the positive charge would feel a force to the right, and the negative charge would feel a force to the left. So I'm really pleased to see that. That seems like a simple thing, but that takes years sometimes and multiple classes for some students to get that. So well done, everybody. That's really good. Yeah, big pat on the back for everybody. I don't know if there's a pat on the back reaction, but good job. Okay.
I have a question. Can you hear me?
Yes. Yeah, I can hear you. Yep.
I don't get, like, with the infinite plane, why the forces is always constant, because wouldn't it, like, dissipate by, like, the square of the distance and stuff?
It only, well, the charge will dissipate. Let's think of a point charge, right? So let's say we have a positive point charge. The electric field will, go away like this, right? So this is the electric field due to a positive charge. The increased space, like as you go further away, tells us that the electric field drops off with distance. For an infinite plane of charge, like in this, there's basically only one direction that the electric field can go. It's away for a positive plate towards for a negative plate. If we have a smaller plate that's finite, then we start to see this behavior. That we get for a point charge like this. Drawing this right. losing track of the number of my arrows here, but so if we have a finite plate, we start to see these edge effects here. But for an infinite plate, you never get to the end. So the field is always perpendicular and it never dies off, even if you get to infinite distances. And that seems unreasonable, but then also our assumption of an infinite plate is also unreasonable because you can't have an object like a plate that's an infinite size. Does that make sense?
Yes, thank you.
Yeah, you're welcome. That's a really good point. Like when we talk about devices like capacitors and stuff, we basically have to assume we're in the region, like in a real device, that we're in the region where the electric field is constant. But really, in a real device that has real size, the electric field near the edge goes a bit wonky. But to make our lives simple, we'll assume the kind of ideal condition, like we always in physics assume when we're trying to learn the stuff, we assume like an ideal point charge with no size, you know, an infinitely thin, like linear charge or a wire. We assume it's got no dimension. I see a raised hand. Yep.
So as you're saying, you only experience the like lowering of the or like dissipating of the electric field at the edges. But if you look at that finite diagram you drew, in the middle, would we consider that an infinite like if we're doing like calculation, would we treat it in the middle as an infinite field since it hasn't experienced that field dissipation that it would at the edge?
Yeah. In a question, well, basically in this class, the simple answer is in this class, we're dealing with infinite planes. That will be the thing, because we don't have the tools to deal with the mathematical tools to deal with more complex situations. So we would have to make the assumption that the field is the same as for an infinite plate or plane of charge, right? So in this class, we're basically always dealing with the ideal, like the field is constant kind of situation for the plate charges and so on. Okay. Or there will be a specification in the question saying, I want the electric field at the midpoint of the plate, like at some point P, then you know it has to be perpendicular there. Okay, we're going to do one of those examples today. Okay, so there'll be something in the question that will take away a lot of the complex math. Math is still hard, but it'll take away the more complex, this edge stuff here. Okay, good. So we're going to do a question here. We just done this poll where we put a positive charge through a parallel plate capacitor, or between, you know, two charged parallel plates. You can see in this picture, we don't have infinite plates here, but we've got parallel electric field lines, which are the red lines. So we're using that simplification right now. The question is telling us that we're using the ideal electric field in here, which is these plates. So you already told me that, and you demonstrated that you understand that a positive plate would feel a force away from, or a positive charge would feel a force away from the positive plate. So as it's traveling through, this is like a kinematics problem, which I know you've done in term 1. So it feels a force in the downward direction, which deflects the charge, just like the force of gravity will deflect like a cannonball or a projectile or something like that. So we're going to do the same kind of derivation, but for a different force causing the, you know, kinematic path. So we've got our plus charge in here. It's feeling, oops, it's feeling some deflection. I have drawn it to hit the plate, but you know, we don't necessarily know if that will happen. We're going to have some direction here. We're going to neglect. Yep. Anyone got a question?
Yeah. Would we neglect gravity? Oh, you just wrote that in there. Never mind.
Yeah. Yep, exactly. Okay. So we've got E in minus Y direction, or J minus J hat direction. Okay. So that means we have no no FC in X direction. Okay, this is just like gravity, except that the force is coming from another physical source, right? Another mechanism. So just like in kinematics problems, we can decouple the vertical and the horizontal motion and acceleration and stuff. Okay. So proton has mass m. The force is equal to mass times acceleration. The force in the x direction is 0. Okay, it's max. So there's ax equals 0. So we have constant flow, constant speed in the x direction. Hopefully that's familiar to you. In the fy direction, we have a force, so we have an acceleration in the y direction. And the force comes from the electric field. So, oops, this is a Q. The Coulomb force is QE, but we know that the electric field between two parallel plates is sigma over epsilon naught, okay? So that means we can combine our force Y is given by the Coulomb force, right? So we can basically substitute this QE over epsilon naught is equal to MAY. We'll do that on the next page. Okay. QE over epsilon naught, oops, equals MAY. We've got magnitudes here. E is down, AY is down, so we're just kind of going with it.
Can I just ask why you just substituted the big E in for the sigma?
Oh, right. That's right. Sorry, I'm getting ahead of myself. I'm combining two equations here. Thank you. This is a sigma. Q sigma over epsilon naught.
Good, thank you.
Okay. So the charge of a proton is equal to E, little e. So we've got MAY is equal to Q, or sorry, E sigma over epsilon naught. Okay. We're going to move the M down here. And we're also going to note that A is dv by dt. It's the definition of acceleration. It's a change of acceleration with time. We're going to define that at t equals 0, Vy will be equal to 0. We're told in the question that the proton is injected into the device horizontally, so there's no y component to the velocity when it comes in. And we're going to call the moment when it enters the device t equals 0. We're going to choose that as our reference point. Okay. So we can, I don't know, have you done this way? I'm going to just write this out. Have you done something that goes like this from here to here? Have you done that math at all? And then you integrate these? Oh, I see thumbs up. Thank goodness. Thank goodness. Okay. This new program stuff has moved around so much in engineering that like a lot of your prerequisites are no longer prerequisites. So we're trying to figure it out as we go. So Vy is equal to E sigma over M epsilon naught times T, noting that Vy is in minus Y direction. Okay. So this is very similar to what you've done for projectile motion, firing things out of cannons off cliffs or whatever you do in your dynamics class. But in this case, the force comes from the electric force, so that's what's giving us the acceleration. Okay. All right. All right, so we've started to think about charges in continuous form when we've been thinking about these plates. So we've sort of subtly moved from point charges to continuous charge distributions by talking about point charges and then infinite planes. So what we need to do is to figure out the math that we need to figure out the electric field due to an object that has charge distributed throughout it. It may not be equally distributed. There might be a function or something that tells you how the charge looks or how the charge is positioned. But we need to move from this discrete form of calculating the electric field to a continuous version. So we change the summation over all charges to look like an integral when the object has a charge distribution that's continuous in space. Okay, so E is equal to K, like this. And the R hat, like in the R represent the position from the source charge in the blob or the object that you're trying to figure out the electric field that it creates. So the R is all of these various position vectors from the source charge to the point where you're trying to figure out your electric field. Okay. And because we're moving to this continuous kind of format here, this tells us that we're likely going to be able to start defining the electric field everywhere using functions. So we can figure out what our charge source looks like and then integrate over that and then get a function that tells us how the electric field looks in a larger region. So we're moving to a little bit more complex kind of way of figuring out the electric field here. Oops, I should put a vector on there. Okay. Does anyone have any problems about smoothing out our lives here?
Yeah, I'm just finishing writing it down.
Oh, okay.
Sorry, are you going to post then the slides with the solutions of the exercise and everything?
No, people requested the slides in advance, so we're posting those now.
Okay.
Yeah. But you can always take a screenshot too. Don't forget you can capture the screen for your own reference. Okay. That's actually a good practice when you're watching a virtual meeting. I don't care if you do a screen capture of this, so feel free. Like a print screen or whatever. Okay. So we've got different kinds of charge distributions. This is just a summary. So when you're looking through your notes, this is kind of a reference for you, but I'm going to show you what they look like. In a volume charge is coulombs per cubic meter. So it's the charge per infinitesimal piece of volume, coulombs per cubic meter. It isn't always a cube. Sometimes it's a sphere. Sometimes it's a little, little bit of a, like an arc length over a solid ring or something. It doesn't always have to be a cube, but it represents charge per cubic meter, per meter cubed. A surface charge is spread in 2 dimensions. So we've got coulombs per meter squared. In this diagram, the little elemental area A is a rectangle or a square, but it doesn't always have to look like that. It could be a little circle or whatever. It depends on what works best for the question that you're working on, but sigma is coulombs per square meter. Rho was coulombs per meter cubed. And then we can have a line charge. Lambda is coulomb per meter. So in the same kind of line about thinking about idealized objects, a linear charge distribution is an ideal line charge. So it has no perceptible width, it just has length. So it's an infinitesimally thin, like linear charge. And the surface charge distribution has 2 dimensions, but it's infinitely thin. in the direction, you know, above and below that plane. Okay. We're going to do a couple of examples here. Oh man, time goes so fast in this class. This one is in the textbook, and I want you to, I'm going to do a different one, which has a little bit different geometry, which is also in the textbook, but I'm going to pick the second one to do for you today. But I want you to take a look in the textbook and try to work through this example because it's described really well in the textbook, in the section on this. And see if you can do it yourself. Like, it's all worked out for you, but it's a good idea to maybe take this slide, which has the question here, and see if you can give it a try yourself. After we do the next one, hopefully it'll make a little bit more sense. But this is a really good question to look at. I think there's maybe a similar one on the assignment, possibly.
Do you know what page that's on?
No, but it relates to figure 23.2, so we're in chapter 23. It's in the main text of the section, yeah, so it's good. Okay, so we'll do this version. This is also in the textbook with a slightly different diagram, but I want to walk you through this because there's some helpful things that like techniques that you should think about when you're doing these questions to simplify your life, which it says on the bottom, using symmetry. So what we have is a line charge. This is an ideal line charge. So it has no thickness, but it's got a length. And it's finite in this case. And it has some like some length 2a. It extends from y equals minus a to y equals plus a. And we're asked to find the electric field at some point p away from the line charge, but at the middle point of the line charge. So this is x or y equals 0 here. Okay. So the reason that we're asked for the electric field at point y equals like some point along the bisector of this line charge is because it simplifies our life a lot because there's symmetry. So there's this piece of charge here, this little elemental piece of charge. So we have some charge density lambda per meter, and then some little elemental length in the y direction of charge. So this is coulombs per meter times a meter. So we would have some little elemental amount of charge here. Okay, and we have the same here. So we have some little elemental bit of charge there. And if we put them at the same, if we consider these being at the same position above and below the x-axis, each of these will create an electric field at point P. But symmetry helps us out here because one of them creates a force that's upward, has an upward component, and the other one at the same distance on the other side creates an electric field as a downward component. So the upward and downward components of the electric field, due to these two little bits of charge here, they cancel each other out. So the only thing that survives is the x component of them. So if we want to figure out the electric field here, just because of the way this problem is set up and the symmetry and the fact that we're looking at the bisector line here, we only care about the electric field in the x component because that's all that exists. Everything in the y component, in the y direction, cancels out here in this particular configuration at this point P. Does that make sense? So we're going to use that Coulomb's force or Coulomb formula to find the electric field. We're going to use this formula here, and we're going to integrate all these little dq's to find the electric field at point P. So what we have to do is set this up. So we've got the geometry right. The electric field is it has some direction, it's a vector. So we've got to figure out what all of these little r's are as vectors when we do our integral. So this here, you can see this is an r. And then we'll have an r here, and we'll have an r here. So we have to basically integrate from the bottom of this line charge to the top, knowing that the r thing, is different for all these little elemental pieces of charge as we sweep through from the bottom to the top to add all the contributors together. So okay, so here only the X component of E survives. Okay, so the symmetry says we only need to do this in one component. Really, we just have to get our trigonometry figured out. Okay, so for every charge element above the x-axis, there's a counterpart below the x-axis at the same distance that will cancel out those y components of the electric field. So the vertical or y components of the electric field all cancel out, and only the EX components add up, because every single charge element here creates an EX in the right-hand direction. So we basically have to add all the EX components from all of these little bits of charge here. All right, here we go. Let's see how we do here. So this is plus A, this is minus A. I'm going to put point P here. Here's our little elemental charge dq. Okay, we have our R vector. This is point P. It creates this little dq, creates a little dE. So our goal is to integrate all these little dEs from all these little bits of charge, from minus A to plus A for this line charge. Okay. So we've got dEx, dEy, and theta. This also is written out in your book, by the way, so you can review this there too. So we want to integrate, which is equivalently summing or adding. Okay. So we want to integrate all these little dq's, and that will, eventually give us our total charge, linear charge density lambda, or some total charge capital Q or something. So in this particular diagram, we've got a little dx, and it's Ke. This is our Coulomb force. Remember, we've got E is equal to Ke Q over R squared R hat. Okay. But we need to do the integral form here. We need to only add the X component because that's the only thing that survives here. So the cosine of dE gives you dEx. And this points us in the X hat direction. Is everybody okay with that? We're writing this out with D's basically in front of the E and the Q. And then we take the X component of it because that's the only thing we need to add up here. Okay, I see some thumbs up. That's good. Thank you, everybody. So this is the Coulomb force per test charge, basically. And this little bit here tells us that we're taking the X component only. Okay, so the cosine basically collapses this down onto the X direction. dq is equal to lambda times dy. So we have some charge density lambda in the y direction, and we times it by a little elemental length dy, and that tells us the little elemental charge dq. In Cartesian coordinates, we've got an issue because we've got r and theta, then we've got an x hat. So we've got to get ourselves all into one coordinate system here. So we need to remember that x is equal to r cos theta. Okay. Y is equal to r sine theta. And r is equal to the square root of x squared plus y squared in this case. Okay. Okay, so y is going to be changing, right? It's a variable. R is going to be changing, it's a variable. But what about x? This is x. So for this particular question here, x is equal to a constant. So we're sweeping through the y direction. So y is changing, and because of that, r is changing, but x is always from the center of this line charge to the point P. Okay. So now we have something we can substitute in for dq, and we have something we can substitute in for r squared. So we can get everything into xy components. Here's, I'm going to go to the next page. So I'm substituting in for my dq. We had a cos theta here, so there's an x component, there's an x variable there. Okay. So we've removed all of our r's and thetas, and we put everything into Cartesian xy components. Okay, so this is a substitution and some combining of terms, but we get here eventually when we put in all of our substitutions for theta and r. Okay, so the total x component of the electric field, we have to integrate dex over the object. Okay, so that means we have to integrate this stuff on the right hand side, right? If we have to integrate the left hand side, we have to integrate the right hand side. So if we want to find the total electric field at point P, we have to sum over all of the contributions of the little bits of electric field that are created by the little elemental charges for the whole object. So we're going to integrate from y equals minus a to plus a. We have ke lambda x over x squared plus y squared to the 3/2 times dy. And remember, x is a constant in this question. Okay, so that means we can pull it out of the integral, which is great. So we have ex is equal to ke lambda x. We integrate y equals minus a to plus a dy over x squared plus y squared to the 3/2. And I don't expect you to be able to do this yet. I think you're still working on this, but you can look this up. There's whole web pages and books that have all these integrals listed in them. Okay. Is everybody following along? I hope you have these math tools in your minds. Okay. Oh, I see a turtle. But I see a thumbs up too. Thank you. Okay, so I'm going to go to the next page here. Don't forget you can take a screenshot before I change to the next page. Okay, just save like PNG files or whatever in your desktop. Okay, so once you look up the integral in the table, and then you substitute your plus a and minus a in, then this is the answer that you get for the total electric field at point P. One thing that we know is that the charge density in coulombs per meter multiplied by the total length of the charge distribution is equal to the total charge. Okay. I see a hand up.
Yeah, in the previous slide, can you show me the integration part?
Which part?
Did you just substitute dy equals to a?
I didn't show it, but this
Okay.
integral, we did it, we looked it up, and then substituted in the limits minus a to plus a, and then combine the terms. Yeah. So give it a try at home.
Okay, all right.
Yeah. Okay. I see another hand up, or is that you? Okay. Any other questions there?
Sorry, why is the X hat disappearing and reappearing at some point?
The X term?
The X hat, the last
yeah.
term to the right.
Yeah. This is the magnitude of the electric field, the magnitude of the total electric field at point P, and we've only been dealing with the X component. So if you want to actually write it as the final answer with the vector, then you know that it points in the X hat direction. So we're doing the math here using just we're adding up all of the EX components in the X direction without keeping the vectors, like without keeping the hats here. So we're just doing the math because we know everything is in the X direction, and then we put the X direction back in at the end. So we're just dealing with this magnitude here. Okay? Because everything is always like all the electric field components point in the X direction, so you can add them up without having to keep track. Okay? Okay. So we've got another example here. Oh, does anyone need to screen capture that? Leave that one for a second. We've now got another question. We've now got another question with a different charge configuration. So here, this blue line is our charge. It's a linear thing. It's a lambda again. And if we take a little, if we take a little component of the charge here, this is dq again, a little piece along this circle, it will create an electric field, a little electric field component at point P. Does anyone want to feel brave and and tell us what you think the symmetry does for us here if this point P is right above the center of the ring, perpendicular, like in a perpendicular direction? What will the symmetry do here for us?
Cancels on X and Y and gives us Z.
Gives us like the net electric field, the total electric field at point P is vertical only. The X and Y components cancel out. That's correct. Okay. Okay. So let's take it down. Oops, that's the worst circle ever. Let's take oh, that's even worse. So let's take a look downward on this ring. We have a little bit of charge. Okay, it's equal to lambda times some length. This is the arc length. This is a little arc length of a circle. Remember, arc length is r times the radius times the angle. That gives you the arc length of a circle. that should be hopefully something you know. So this is our density, and this is our little infinitesimal length of the circle. Okay, so that gives us our little charge that we want to deal with. Theta goes from 0 to 2 pi. Okay. To do one full circle. Like if we're integrating over this charge distribution, we have to integrate theta from 0 to 2 pi. Okay. We only have EZ components that survive at point P. Okay, so at point P, EX is equal to 0 and EY is equal to 0, because for every piece of this charged circle on one side of the circle, there's a charge on the opposite side of the circle that's giving us the horizontal component in the opposite direction. So again, only the vertical component survives here. Okay, and if we look here, so we've got DE and we've got Z. I should get rid of that logo there so I can draw there. Okay. We've got some angle. In this case, it's called phi here. Okay. Got some angle phi. So DEZ is on this side. This is DE horizontal over here. Okay, so DEZ is equal to DE times cosine of phi Z hat. Okay, so we take the cosine here to get us this side of our right-hand triangle. Can people see where I got that from? Someone just left the meeting. I don't know how to take that. Okay.
Can you explain that part one more time, please?
Okay. Which part? Just the cosine phi part?
Yes, please.
Okay. So I'm basically redrawing this down here. So this is our point P right here. So we've got some electric field component from this little charge element here. Okay, so there's electric field that's created by that little charge bit there. And this angle that the charge element makes with the z-axis is the same angle that we have on the other side. These are, where do they go? They're not complementary angles, they're the other ones. Supplementary angles, I don't remember. Parallel lines, you've got these two angles are the same on both sides. So we've got our DE here that's produced by this charge, okay? We've got our Z direction, and the only electric field component that we care about is the vertical part of it, because that's the only thing that survives this integral process, this integral, this integration, okay? So we want to figure out what the Z component is, knowing that we have a right triangle here. So the adjacent side to this angle is related to the hypotenuse of this triangle by the cosine. Okay, adjacent over hypotenuse is cosine of this angle. The opposite side of this triangle is related to the hypotenuse by the sine of phi. So if we did the math here, this is DE cos phi, and this is DE sine phi. So when you break this triangle down into its perpendicular components, knowing this angle here, this is what you get. Is that okay?
Yeah, I'm just having a hard time following your cursor, so I just get confused
Oh,
kind of where
okay,
we're
okay.
referring to.
Oh, I apologize for that.
That's okay.
Does
Thanks for
that help
explaining.
though? Does that
Yes.
help though? Okay, great.
Thank you.
You're welcome.
Yeah, I think your cursor is frozen. At least it is on my screen.
Oh, oh
Yeah,
no,
that's
not
what's
good.
happening with me as well. So I don't know what parts we're looking at
Yeah.
while you're explaining it.
Okay, I'll try to use my words, as they say, for little kids. I'll try to do that. Thank you.
Okay, thank you.
It's working great here, so I can't tell. I'm sorry about that.
That's okay.
Okay. So we have KE DQ. Oh, I forgot to say too. Oops. This distance R is R squared plus Z squared. Okay. So when we do the R in the electric field equation, like the 1 over R squared part, this is that. Okay. So this is the distance between the charge and the point where we want to calculate the charge. So in our KQ over R squared formula, this is what you need for the R squared. Oh, you can't see my cursor. This is what you need for the R squared in the electric field formula. Okay, so we'll put that in. And then we take the cosine of that. So we only want the Z component. So this is this part here is like the total, the full vector electric field that you'd see there at that point P, and then we do the cosine phi to get the Z component of it. So we do KE lambda R d theta over R squared plus Z squared cos phi. Okay, Z is constant because it's just a fixed position above the ring. R is constant because the ring has a constant radius. Phi is actually constant in this question because this position on the ring with radius R, capital R, this position P, that's the same magnitude for all points on the ring. Okay, so capital R is a constant and Z is a constant in this question. Okay, so capital R is constant, Z is constant, R is constant, and because Z and R are constant, so is cos phi. And then d theta goes from 0 to 2 pi. I see a hand up.
I just want to double check that I'm thinking about this right. Like when in this example, in the last one, when you say like DE, you're just looking at the small chunk of the electric field that's being affected by that small chunk of the ring that we're looking at, right?
Correct. The little dE is produced by the little dQ, which is here, right?
Okay.
So it's this little bit of charge on the ring is producing a little bit of electric field here.
Right.
And to find
Okay.
the total electric field, you have to add all the bits, all the dEs from all the parts of the ring.
Okay. Perfect. Thank you.
Yeah, you're welcome. So we can set this up. We integrate theta from 0 to 2 pi. KE lambda R cos phi R squared plus Z squared d theta. Okay. These are all constants, which is it. Oh, can someone mute themselves? Olivia, I think your mic is off, unless you want to talk. Okay, these are all constants, so they move outside. Okay, so we pull all the constants out. This turns into actually a very simple integration. It's just equal to 2 times pi. And then you can do a whole bunch of manipulation, and this is written out in the textbook for you. So I want you to look at this example. We don't have time to do the math today because somehow we only have 20 minutes to do. But E, unfortunately, so there's some work happening here, but the textbook writes it out really well. We have EZ is equal to 2 pi KE lambda RZ over R squared plus Z squared to the 3/2 because cos phi is equal to Z over Z squared plus R squared. So we've made a substitution in there. Okay, so basically we've just done the 2 pi and then substituted in for cos theta, and you get to this answer here. Okay, so this is done in the textbook for you. But I wanted to make sure we discussed how you set it up, because the setting up part is the biggest challenge here. Okay, so take a look in the book. It's written out in a lot of detail, so, and there's a lot of words describing it, so hopefully it makes sense. There's another example in the textbook here, and I actually found a YouTube video of someone working through it, so you can read it in the textbook. You can watch someone work through it for you, and I think he also does the ring charge as well. So if you want a different perspective, someone else telling it to you in a different way, you can search his YouTube channel, and he has a link to it in this video. You can see the example we just did, and then for the case of a solid disk, you basically take the answer that you got for the ring, and then you integrate over a whole bunch of rings to get a solid disk. Okay, has anybody got any questions there? So instead of talking about it in class, I recommend you read that in the book, in the textbook, and then this is an additional resource. You can just, like, it seems like a pretty good explanation. And he has some other derivations too. You can always Google electric field of disk in YouTube, or you can put it in YouTube and you'll find a lot of examples. This one seems pretty good. Seems pretty consistent with how we talk about it with our textbook. Okay. All right. Now we're going to talk about electric flux, which sounds kind of Star Trek-y, but electric flux is related to this concept of the electric force field or the electric field. We have electric field vectors that we can imagine in space everywhere. Like there's charge in the universe, so there's going to be electric field everywhere. What we want to do is try to make use of that to see if we can, use the electric field to figure out something about the charges nearby. So that's what this part of the course is about. So we have electric field lines. They represent the electric force on a unit charge. The electric field lines can't cross because that means you'd have two possible forces in one location, and that's not possible. Forces have to add up and give you a total, and then there's one force. So electric field lines can't cross each other. They can, they have end points. They start on positive charges and they end on negative charges, but they can never cross. Because that would mean you'd have an ambiguous two possible forces acting on an object, which isn't possible. The strength of the charge producing those electric field lines, or the magnitude of the charge producing those field lines, is related to the number of lines that you draw. So the charge on the left, the positive charge on the left, has a lower charge than the charge in panel B, because the charge in panel A has fewer lines coming out of it. Okay, so the number of lines is proportional to the charge. So that means that if you can count the number of lines, it'll tell you something about the charge. So that's what we're doing. We're going to try and figure out a way to count these lines, and then it'll tell us something about the charge there. Okay, and then we can also kind of do a loop. We'll think about these electric field lines, and then we'll talk about we'll get to some charge value that's producing those electric field lines, but then we can kind of circle back to the electric field. So there's some math and stuff we have to learn how to do here. Okay? So the electric flux is defined, it's basically a count of the number of electric field lines passing through surface area A. The dot product is used here. Hands up if you've covered dot product in your courses or you're doing it now. Does anyone know what the electric or the dot product tells you, or what it's useful for? Oh, I see thumbs up. So what is the dot product? What's the point of the dot product? Like, you probably know the formulas and stuff, but what's the point?
It is the projection of the vector on another vector.
Mm-hmm. Right. It basically gives you the component of one vector in the direction of another vector. So it collapses this problem down into a one-dimensional problem, kind of, or like it basically puts these two vectors. We're trying to count the number of electric field lines going through a surface, and the surface area is defined by a vector perpendicular to this surface area. So we want to figure out how many electric field lines are pointing through the surface. So how many electric field lines are parallel to A, the unit vector in the direction of this, like perpendicular to the surface, right? We want to collapse the electric field vector and figure out, not collapse, but we want to figure out the component of E in the direction of A. That's basically what we're using the dot product for here. Good. Okay. And we're using that dot product as a tool to count these electric field lines. And the electric flux is given by this, it's given by this Greek letter here, which may or may not end up being a COVID variant name. I don't know, but it's called phi or phi, depending on how you like to say it. Okay. You can see here in this figure here, we've got two surfaces. One is like vertical in the back here, and then one has an angle. So you can see that electric field lines can pass through surfaces not only in the perpendicular direction, they can have an angle with respect to it. When we're calculating electric flux, we don't care about the electric field lines that pass tangent to the surface. We only care about the ones that go right through. So we're looking for this perpendicular bit of it. Okay. So we have the flux through surface A1, which is this one on the left, is E dot A1. And A1, it's not really drawn here, but A1 is a vector perpendicular to this back surface here. So E and A are parallel to each other. So E dot A is just E times A, because there's no angle between, they're parallel to each other. Case 2 is drawn a bit weird. This normal doesn't really look normal, but we'll assume it is. E dot A2, because there's an angle between the surface normal and the electric field, the dot product has this cosine term, right? So E dot A2 is EA2 cos theta, but A2 cos theta is just A1. So we basically have the same number of field lines passing through A1 and A2, which is exactly what we want, because the same number of E vectors do pass through there, okay? If we multiplied E times A2 without the dot product, we would get a larger number. But we only want to count the electric field lines that are going through this. If we get a larger number, we don't have more field lines going through, it means we're not counting them right. Okay, so if we don't take into account the angle between the normal direction and the electric field, then we get the wrong amount of flux, because the same number of field lines are passing through the back as they are through the front here. Okay, does that make sense? We're basically counting electric field lines this way. And we use the cosine to make sure we're only talking about the perpendicular component of this. We want to calculate the perpendicular component of the field going through the surface. That's basically what we're going to do here. Okay, so that's the goal of this. So we choose a direction. We want to be consistent. We want to choose only one side of the object. So in all of these, just very briefly, we have, you know, normal vectors to the left and to the right. We want to be consistent and always choose the normal direction consistently so that we can count electric field lines coming in and going out consistently. We've got to just keep, we've got to keep our direction straight. Otherwise we're adding negatives and, you know, subtracting positives, and that doesn't work, okay? So the flux going into a surface is going to be called negative, and the flux coming out of the surface where the normal vector is out, the electric field is out, that's going to be positive, okay? So the flux on this side is positive, and the flux on this side is negative. And you can see that we've got flux going in and flux coming out, right? So we're wanting to count the field lines going in and out, and the number of field lines is proportional to the charge. So if we have charge inside here, we kind of don't care about the field lines, you know, coming from charges outside. We've got to make sure, we've got to get a tool ready to be able to sort of count the field lines in a consistent direction to try and understand what charges are inside that shape producing the field lines. Okay, that got a little bit off the track, so I apologize about that. Hopefully that makes sense. We choose the normal direction of the surface outward, and then we have to be consistent with that so we know if we're counting field lines going in or out. That's the point here. There's a video you can watch that will hopefully explain that in a different way if you need it. In this example, it's kind of drawn weird because we don't really draw electric field lines like this, but we've got a positive plate down here and a negative plate up here. We've got electric field lines going from the positive plate to the negative plate, and they're passing through a cubic surface. Basically, the question here asks what is the flux, the total flux passing through this object. Okay. Does anyone have an intuitive guess what that would be? It's actually zero because we have the same number of field lines going in as we have going out. But I'll show you how it goes. Okay. So through the bottom surface, we have an area A squared, and the surface area is in the minus Z direction because the outward direction of the surface is down, and we have an electric field pointing up, so our flux is negative here. On these sides, there's no flux. Does anyone know why there's no flux there?
Because we have to keep our direction constant.
Yeah, the normal direction of this surface is out, is to the right. So x dot z is 0. The electric field is parallel to this surface, so no electric field line passes through this surface. Does that make sense? So the flux through all of these side surfaces is 0. E is parallel to the surface, which means it's perpendicular to the normal outward normal direction. So E dot A is 0 there. On the top surface, we've got E up and the normal direction up. I should say A. Those are parallel, so we have a positive flux here. Okay, so we have field lines going in at the bottom, which is negative flux, and out at the top, which is positive flux. Okay, when you add those together, you get 0. This is a question that people tend to overthink. So it's simple in terms of its math, but it's only simple as long as you remember you're counting the electric field like passing through or penetrating the surface. So on the sides, the vertical sides, there's no flux. But on the top and bottom, there's flux, and it's negative on the bottom and positive on the top, so it's a total of 0. Okay. If we want to figure out the electric flux due to a charge, point charge Q, we can put a sphere, a radius capital R, around it, and we basically want to calculate, we basically want to count the number of field lines passing through this point, or passing through this sphere. The electric field is radial, right? And the surface normal direction here is also radial. So if we're clever with our surface, then E dot A becomes E times A. As long as E and A are parallel, life gets easy. The dot product is just a multiplication then, okay? So for a point charge, E is KQ over R squared R hat, right? Does anyone know what the surface area of a sphere is?
4 pi r squared.
4 pi r squared. Great. I'm a little overexcited, but thank you for doing that so quickly. And in this case, we have capital R. It's a constant, right? So the flux the electric field dot A. In our case, E and A are both radial. They're parallel. E has the same magnitude at all points on the sphere because we have a constant R. Okay, so the electric field is the same value everywhere on that surface, so we don't have to worry about E being different in different places. So we get 4 pi r squared, that's our A, times KE Q over R squared. Okay. KE is 1 over 4 pi epsilon naught. So you could rewrite this as 4 pi r squared, 1 over 4 pi epsilon naught Q over R squared. So R squared cancels out, 4 pi cancels out. So phi is equal to Q over epsilon naught. So there you go. Pretty straightforward. I'll leave that there so you can screenshot that if you want to. This is interesting, at least to me, because the flux is proportional to Q. So if I put a charge of 10Q inside that sphere, I have 10 times the flux. If I put, 0.33 Q in there, then I have 0.33 of the flux, like a third of the flux. So the flux is proportional to the charge enclosed inside that sphere. And that is like the next big important thing that we got to know. Like the flux, we've looked at this thing called flux, but then we got this situation where we realize, oh, it's actually related to the charge that's producing the electric field. And we can do it using something that's a scalar, not a vector, which is kind of nice too. Okay. You can do more calculus here. This is how you do it if you want to do more calculus. But symmetry is our friend. And because we know that E is parallel to A everywhere, we can simply multiply the surface area by the electric field magnitude everywhere. So it's nice. Does anyone have any questions about that? No? Okay. So this basically illustrates the idea I'm talking about. If we have an electric field coming out, whatever our surface is, we would pick a sphere because we're clever and we know that symmetry is our friend. But the number of electric field lines passing through this blobby pink surface tells us that they're like the flux is positive, it's outward. So we have a positive charge inside. If we have the opposite sign of charge negative in here, the flux, the field lines all go in. So the flux is negative because we have E in dot A out. So the flux is less than 0 here, and the flux is greater than 0 here. So the sign of it tells us if it's a positive or negative charge, and the magnitude of phi of the flux tells us how much charge is in there. So what we're going to do is to practice picking these shapes of these surfaces to calculate that flux value and then figure out what the charge is inside. Or to use the flux to find the electric field due to the charge inside. Okay? Are we okay with that? It's very quiet. I assume we're all okay. Okay, good. Thanks, everybody. That's all we've got for today.
Sorry, I didn't get to take the screenshot of the first exercise. I don't know if you can put it.
Which
please.
one? Like right at the very, like way back?
Yeah, way back.
Okay.
Thank you.
Which one? This one?
Yes, thank you.
Okay. Yep. I think there's more. Is there more page? Hang on. Oh, sorry. There's more pages, so let me know when I go to the next one.
Yeah, sure. Thank you.
Yep, you're welcome. Thanks, everybody.
Sorry, I had a question about when you were deriving for the electric field, like for the ring and disk questions.
Okay.
We used symmetry, and a lot of the time we kind of assumed variables were constant.
Mm-hmm.
If that's not the case, does that like complicate it even more, or? Because it was kind of hard to follow for the like this example. So
yeah. In the way that this question is set up, we're given a point P at some position. So this distance is fixed. That makes this distance Z constant. Another question might ask you to find the electric field as a function of Z. So for some various, we're not doing that in this class, it's too complicated. But we're told that position P is here and it's located at position Z, and that this ring is fixed here. So this ring distance and this distance to the point P is fixed by the question. So that makes it a constant, okay? And then because Z is constant and the ring radius R is constant, it makes this triangle the same. Like as you rotate that triangle around the ring to add up all your DQ like bits, that triangle stays the same. It just sweeps around the ring. So phi, this phi, is a constant as well because it's related to this triangle that doesn't change. Does that make sense? So for this question, just the way that it's set up, those variables are not variables, they're constants. A more difficult question could have them varying.
that kind of makes sense.
Kind of. And then so here we've got the ring, right? So the ring radius capital R is fixed, but in the disk here, R, like we've got like a little ring element here, that now becomes a variable because we're going to integrate from the center of the ring out. So we're basically going to take these triangles here that we were talking about, like the Z and the R. Oh, you can't see my. So we're going to take this triangle and we sweep it out through 360 degrees or 2 pi angle. But then we got to do it for the next ring, and then we got to do it for the next ring. So this triangle becomes different size every time we find the contribution of all those little charges and all those little rings, we sweep them out. So that distance from the Z-axis to the little elemental charge we're talking about changes now. It goes from 0 to plus R. So it's not a constant anymore. That probably makes it more confusing. Does that make it more confusing or less confusing?
No.
So in this case, Z is constant here.
The DQ and DE Oh, what?
Sorry, go ahead.
Like for DE and DQ, those would be their derivatives because they're just like the tiny parts of like I don't know, the charge and the electric field, right? That's why it's okay.
Yeah, we
Okay,
use a
then, yeah.
D to denote that it's a little like infinitesimal part. And when we integrate over all of the little DQs, we get total Q. So the little d is representing that it's just an infinitesimal part, and we've got to basically add all of them up to get the whole charge, or all of the e's, like the little de is just a little bit of electric field produced by this little bit of charge. So our job with the integral is to add up all of the contributions, like add up all of the electric fields due to all of the little dq's.
Okay, thank you. That clears it up.
Oh,
Appreciate
good.
it.
Okay, great. Another hand up here?
Just so for this example here, the r wouldn't be constant, so that would mean that cos theta wouldn't be constant either, right?
Correct. Yeah.
Okay.
In this case, like this capital R is constant, but it's not in the integral. This is a limit of your integral. So you're going to integrate from R equals 0 to R in this case. So when you set up your equation in the integral, it's going to be a function of this R, which is this hypotenuse of this triangle, because that's the distance between point P and this little dq that you're looking at.
Okay.
Does that make sense? Yep.
Hello.
Hi.
I have a question. What is the exams gonna be like? Like how many questions? What style of question?
Yeah, there'll be longer ones like this. Like we don't anticipate multiple choice, for example. So we're gonna have I haven't said it yet, but we're gonna probably have 3 questions. You might be asked to derive an equation. You might be asked to do a calculation, or both.
Okay.
Yeah.
Also,
we're gonna try to not make the math so difficult. So, symmetry is something you got to keep track of. If the question is getting too complicated, you've probably missed some symmetry.
okay.
Yeah.
Also, are we allowed to like bring things in if it's like in person, like, bring papers in with notes on them?
Well, we'll let you know in advance. We'll let you know before the test what you can bring, but basically you can bring a basic scientific calculator that doesn't have internet and doesn't have graphing, and you can bring pencil, pen, eraser, ruler, like very basic, and we'll give you the paper. So you're basically using your memory and your pencil, more or less. Yeah.
Okay.
So no cheat sheet at all with any equations?
You will be provided with a formula sheet, and we're just finalizing it right now. We have to make sure we've got the same notation as the textbook. We changed textbooks this time, so we have to make sure we've got all our variables consistent with the book. So we'll be releasing that hopefully next week, so you can do homework with it, so you can get used to it, but you'll have a formula sheet with the exam.
Okay.
And we'll let you know that before the exam for sure. We'll put out an announcement to everybody.
Okay, that sounds good. Thank
Yeah,
you.
you're welcome. Yep.
For the 7th question, which you have to submit separately, is there any format for the working, or like
for how you put it out?
Mm-hmm.
Yeah, no, not really. Just put enough detail in there, or enough explanation so that the marker can understand your reasoning. Yeah, if the marker can't see how you got from one step to the next, we don't know if you just copied from a textbook or something, or from a
Okay.
or whatever. So enough to show that you understand what's behind.
Yeah, so like writing the formula and then substituting it in, and then like step by step solving it. That's it, right? There is no other thing that we have to do. Like,
Yeah, basically how, like, write it for us, like you like us to write it for you, kind of.
okay, fine.
Quite as
Yeah.
much detail, but
Nah,
yeah.
it's okay. Thank you.
Yeah, you're welcome.
So we've now learned everything enough to be able to do the full assignment?
Oh no, we don't quite. I think there's a question. I hope we get through 2 more examples today, But we will do them on Monday for sure. So you might not be able to do one or two of the questions.
Okay.
Well, you might be able to do them with the textbook, but we haven't covered quite everything yet.
Okay, sounds good.
Yeah, but it's due on Wednesday, so you can get everything else done.
Right. Yeah.
Yeah. Okay. I'm gonna go now. Thanks everybody. Have a good weekend.
Thank you.
Thank you.